Hi, grade 11s. Today we're going to take a look at the factored form of a quadratic equation or quadratic function. Okay, we spent the last couple days factoring because we need the factoring piece to be able to do this piece today. So I'm assuming that you're all factoring experts, so let's get to it. This example right here says, sketch the graph of the quadratic function x squared plus 4x minus 12, state the domain and the range. So what we need to do is we need to take this and factor it, obviously. So this is a pretty simple trinomial, so there's nothing too crazy happening here. We're looking for two numbers that multiply to negative 12 and add to positive 4. So that's 6 and negative 2. So that's x plus 6, x minus 2. So from that, what we have to consider is what value of x makes that 0. And what value of x makes that 0. Now, the first bracket, negative 6, would make that 0. The second bracket, 2, would make that 0. Now, you might think, well, how's Hutton doing that? Well, if we set x plus 6 equal to 0, and just solve for x, we'll bring the 6 over and get negative 6. Likewise here, we have x minus 2 equal to 0. Bring the 2 over, becomes positive. So the values of x that make each of those brackets 0 are negative 6 and 2. Now, so what does that mean? Well, what that means is I'm going to take my graph and try and make it bigger, because holy Hannah, it's a wee bit small, isn't it? There you go. It's a little bit bigger, a little bit more manageable now. Negative 6. So we have to find negative 6. And remember, when I was marking your stuff, I saw that there was a lack of labeling. So get that labeling going on your axes, just so I know exactly what's happening. So negative 6 would be right here. 2 would be here. Those are the zeros. What else do I know? Well, if I take a look at this, I know that A is positive, so it's going to be pointing up. So it's going to roughly look like a parabola pointing up. The question might be, where is that vertex going to be? Well, where is that vertex going to be? It would be, it would probably be, now the thing is if we want to sketch it here, what we have to understand is the axis of symmetry is going to be located halfway between those points. So the axis of symmetry is going to be right here. Okay? Now we know the vertex is going to be somewhere on that axis of symmetry. Okay? So the question is, what's the y coordinate? So what we have to do is we have to find the y value of the equation. So we know the x value is negative 2, which is halfway between those two zeros. So we're going to plug in negative 2 plus 6, negative 2 minus 2, and we're going to get 4 times negative 4, which is negative 16. So negative 16, which automatically makes my scale go out the window. That's fine. I can make a new scale, and my new scale is going to go 4, 8, 12, 16, 20, negative 4, negative 8, negative 12, negative 16, negative 20. And now all of a sudden I'm going to have a point, negative 2, negative 16, which will be right here. Okay? And again, I'm going to have that point, and I'm going to have my parabola pointing up. So it's going to look like that. And it's going to look like that. There's my parabola. Okay? There's a nice sketch of my parabola. Now, it says to state the domain and the range. So the domain are all possible x values, and in here, with a quadratic function, there's no restrictions on the domain, so we would just say negative infinity to infinity. Now, when some of you are doing this is a bone of contention here. Here it is, okay? When some of you are writing out your domain and range, if you're going to say negative infinity to infinity, well, whatever you're going to say, the lower number comes first. Negative infinity is lower than positive infinity. So it has to go negative infinity to infinity. The other thing is that because it can't actually equal infinity or negative infinity, you're going to put round brackets on them, not square brackets. Square brackets are only if they can actually equal that number. So round brackets for the domain here. For the range is a little different because there's a minimum. The minimum value is negative 16. So we're going to go and we're going to put a square bracket at negative 16 because it can actually equal negative 16, and it goes all the way to positive infinity. So we'll use a round bracket there. So there's your domain and range, okay? So the domain is negative infinity to infinity, and the range is negative 16 to infinity. Alright? So what you saw is we graphed that, and we didn't even touch a graphing calculator or a piece of software. We just used our noggin and our knowledge of factoring. So we're seeing where that factoring is helping us take a peek at what a quadratic function looks like. Alright? Okay, next one. Use partial factoring to graph negative x squared plus 4x plus 20. State the domain and the range. Because if we try to factor this, looking for two numbers and multiply to 20 or negative 20 and add to 4, the only two numbers that multiply to 20 are 2 and 10 and 5 and 4. Neither of those have a difference of 4. So it's back to the drawing board. So if we're going to go ahead and do that, first thing I want to do is I want to make this graph bigger because, hey, it's not. So there you go. Partial factoring here. So what's that going to look like? Well, what's partial factoring? I'm going to just focus in on those first two terms. And I'm going to take a factor of negative x out. And when I take a factor of negative x out, I'm going to be left with x minus 4. And I still have this 20 over here. Okay? I still have that 20 over here. Now what does that mean? Well, again, what I'm going to look at is what values of x make both of these expressions equal to 0. So clearly the first expression is 0 when x is equal to 0. And the second expression is 0 when x is equal to 4. So what does that mean? Well, the importance of this plus 20 comes into play now because at the x values 0 and 4, the function has a y value of 20. That's the whole meaning of the partial factoring piece. And the other thing we know is that this thing points down. So we better make sure that we can allow for that, because I don't know what our y scale should be, but what this does tell us is we have the points 0, 20, and we have the point 4, 20. So we know that somewhere at right smack dab in the middle, so at x equals 2, there's going to be our vertex. And we don't know what it's going to be, but we know it's going to be higher than 20 simply because there's a maximum, and the maximum is only at that one point. So how do we find out what that point is? Well, we can plug in this x value of 2 into the function. So if we go ahead and do that, we have y equals negative 2 times 2 minus 4 plus 20. So y equals negative 2 times negative 2 plus 20. So that's going to be 24. So we know then that the vertex is at 24. So we can make our scales using that information. So how am I going to do that? It doesn't have to be anything fancy. So what I'm going to do is I'm just going to go 5, 10, 15, 20, 25, negative 5, negative 10, negative 15, negative 20, negative 25. All my x values are under 5 for that matter. So I'm going to go 1, 2, 3, 4, 5, and negative 1, negative 2, negative 3, negative 4, negative 5. So now it's just a matter of plotting my points. So I know I have 0 and 20. So 0, 20 is right here. There we go. I've got 420. That's right here. Actually, I'm really not liking that choice of making those x values go up by 2s, or rather go up by 1 every 2 squares. So I'm going to change my mind on that and just put a 10 here and a negative 10 here. Sorry about that, because if I look at the clear picture here, we're going to have 420. So there's 4. and there's 20, so it's going to be like right here. And we're going to have 2 and 24, which would be like right here. Now we don't know where those zeros are going to be. Okay, we don't. But so what we can do is just draw, like I said, just draw a sketch. So the sketch is going to be, it's going to go like this, and it's going to go like this, and that's about all we can know. But we do know those key points, right? We are able to identify those key points. And by knowing those key points, knowing that the quadratic points down, we can have a sketch of this. And we have enough of a sketch so that we can figure out what the domain and the range are. And that's what's important here. Okay? Alright, so let's talk about the domain and the range. So when we talk about the domain here, domain is the same as the last one. I don't know why I've got set notation out. We could do it that way, but I'd rather not. We're going to go negative infinity to infinity. And the range is going to go from negative infinity to 24, including 24 though, so square bracket on the 24. Okay? So there's our graph, and there's our domain and our range. Alright? So when we're doing our partial factoring, what we're doing is we're only taking a look at the first two terms of the trinomial, and we're taking out, usually we're just taking out x, but we took out negative x in this case because we had negative x squared. And the two values we get, 0 and 4, at those two values, the y value is going to be whatever's left over here. So we got 20 there, so you're going to have 20 here and 20 here. Okay? Alright, so going on to the next example. Find the quadratic equation that's graphed here. So here we're given a graph. We're asked to find out what is the equation. So here's what I know. I know that equation is in the form y equals some number times x minus r times x minus s. What is r and what is s? R is one of the roots, s is the other root. A just determines the direction of opening, and a also determines how skinny or not skinny the graph is. So if I take a look at r and s, r is obviously 0, s is obviously 6. So the equation is going to be something in the form of y equals a x minus 0, x minus 6. Okay? Now I don't have to put x minus 0. I could just say y equals a x times x minus 6. Now, what I need to do now is find some other point on the graph where I definitely know the x and the y value. I'm going to pick this point right here. This point right here is 4, 4. And I can plug in 4, 4 in for x and y and solve for a. So y is 4, x is 4. X is 4. So we get 4 equals 4a times negative 2. 4 equals negative 8a. A equals negative 4 over 8. How do I like that? Not bad. Gonna simplify it. That's negative 1/2. So I look back at what I had a wee bit up here. This y equals a times x minus 6. And I'm going to take this a value here and plug it in there. So y equals negative 1/2 x times x minus 6. That is the factored form of the quadratic function pictured in the graph above. Okay? So we plug in whatever those roots are for r and s. Then we find some other point on the graph where we definitely know the x and the y coordinates, plug them in for x and y, and solve for a. A is negative, and that makes sense, right? It makes sense that a is negative because it points down. Okay? Alright. I think we have one last example. And it's a goodie. Student council raises money by putting movie nights on in the gymnasium. They charge $4 a ticket. At that price, they sell 48 tickets per night. From previous weekends, they know that for every 50-cent increase in price, 4 less people will attend. What should student council charge in order to maximize the revenue? So, a lot of different ways that we can take a question like this, okay? But if we're going to use the strategies that we're looking at in today's lesson, what we're going to do is we're going to look at some kind of a relationship. So I'm going to say, we're looking at maximizing revenue, so I'm going to let, I know that just in general, revenue is going to equal the number of tickets sold times the price of a ticket. Okay? Now, if we look at this, I can look at it this way. The revenue, I'm going to let it be R. Now, if I look at the number of tickets sold, there's 48 tickets sold usually. Okay? And the 48 tickets are sold when the price is $4 per ticket. Now, the relationship is every 50-cent increase, 4 less people are going to attend. So this is how we develop this formula, this function, this relationship. If we add 50 cents, we lose 4 people. So, this relationship can happen no matter how many times we jack the price up 50 cents. There's going to be 4 fewer people attend than attended for the last time the price went up. So what we don't know how many times we're going to jack the price up, right? So we're going to call that X. So for however many 50-cent price increases, there's going to be 4 less people showing up. Okay? Now that number, to maximize revenue, that number might be 0, it might be 5, it might be -4. In other words, to maximize revenue, you might actually have to lower the temperature, not raise it. But we don't know that. Okay? So this relationship is between 2 things, the revenue and the number of price increases. And X represents the number of price increases. So let X represent the number of price increases. Okay. Now, what we need to do is we need to factor these. In other words, we need to take each of these relationships and solve for X. Okay? They're already factored. It's already factored for us, right? So if you take a look back at that first question, okay? This wasn't factored for us. We had to factor it, then we solve for X. So looking at our question here, the tough part was coming up with this relationship. We did that. Now we have to factor it, finish the factoring. So from here, I know 48 minus 4x is 0. So 4x is 48. So x is going to be 12. So that's going to be one of the zeros. In other words, when x is 12, they're making no revenue. Because there's going to be no people there, right? Because this right here represents the number of people that buy tickets. And when this is equal to 0, nobody buys a ticket. Okay? So obviously we can't jack the price up 12 times. Okay. If we look at the other relationship here, we want to see when 4 plus 0.5x is equal to 0. So 0.5x is equal to -4. X is going to equal -8. What does that mean? Well, that means that if we lowered the price 50 cents 8 times, we would be giving the tickets away for free. Obviously, you're not going to make any revenue if you do that. So these are our zeros. So if we took a look at a very rudimentary picture here of what's happening, what I know is that I have a 0 here at 12, a 0 here at 8, and somewhere in between. Oopsies, that's negative 8, my bad. Somewhere in between these two. And what would be the in-between point? Well, that'd be 2, right? So at 2, just put an axis of symmetry here so it kind of makes some sense. So somewhere up here at 2, doesn't really matter where, right? This relationship's going to look like this. Okay? Now why that's important that we know that this is 2 is that 2 is special. Well, what do you mean it's special? Well, that 2 is going to be the number that maximizes the revenue. And that's what we're looking for. Now, that doesn't answer the question, because the question isn't how many times do we increase the revenue, the price to maximize the revenue. The question is, what should they charge in order to maximize the revenue? So we'll get there in just a minute. Okay? We'll get there in just a minute. But we know that x is equal to 2, and that maximizes the revenue. And what does x represent? X represents the number of price increases. So that means that we increase the price twice, and that will maximize the revenue. So let's go back to our original expression here. Okay? In our original expression, this right here represents the price of a ticket. 4 plus 0.5x. So if we take a look at that, if we take a look at the price as 4 plus 0.5x, and we know that x is equal to 2 in order to maximize the revenue, 4 plus 0.5 times 2. So we get $5. So $5 is the price that they should charge to maximize the revenue. Okay? $5 is the cost that maximizes the revenue. So, therefore, is it student council? I don't know. Is it student council? Yeah. Student council. Student council should charge $5 to maximize revenue. Okay. Now comment. That question could be asked different ways. What do I mean by that? Well, I could ask, what is the maximum revenue? And if I do ask, what is the maximum revenue, then we have to look at this formula. That the revenue is equal to the price of a ticket, which we already know, it's $5, times the number of tickets sold. So to worry about that, then I'd have to look at this relationship, the number of tickets sold. Okay? Because if x needs to be 2, then how many tickets would we sell? Well, I'm just going to make some extra room here. At max revenue, the number of tickets sold would be 48 minus 4 times x, but in this case, how do you make an 8 backwards? There we go. X is 2. So in other words, at that exact point, the number of tickets sold is 40. So if we wanted to know how many tickets would be sold when we maximize revenue, the answer would be 40. But now, what is the max revenue? Well, the revenue is going to be the number of tickets sold, which is 40, times the price of a ticket, which is $5. So the maximum revenue for student council would be 200 buckaroos. Max revenue. So that this point up here is 2 and 200. That's the maximum revenue. Okay? So there's a lot of things that can fall out of this question. This particular question was only asking, what should student council charge? Well, the answer to that question is just $5. Okay? But if we ask what's the maximum revenue, then we need to find out how many tickets were sold and then multiply that by the price of a ticket that maximizes revenue, and we get $200. Okay? So there's a lot of different questions that we can ask here. But the only question that was asked here was, what should they charge? And the answer is, they should charge $5 to maximize the revenue. Okay, so for homework, you have pages 391 to 394, numbers 1 to 17. Now, I'm just going to check here if you have a quiz. Just give me a second here. Okay, so it looks like that you don't have a quiz on this stuff. All right, so it looks like you don't have a quiz on this stuff, but I don't know that I like that, so I think I'm going to actually make a quiz on this stuff. So we will have a quiz on this stuff on Monday. All right, have a great weekend.